Okay, so let's assume that we want to know the elevator angle when the aircraft speed is 125 feet per second. So in that case, first we should calculate the lift coefficient. The lift coefficient is given by lift divided by the dynamic pressure times the wing planform area. Now the lift is equal to the weight of the aircraft, which is given to us 2,750 pounds, and density is equal to 0.002377 slugs. This value assumes that the aircraft is flying at the sea level, and the planform area is also given as 180 feet square. So the value of lift coefficient to two decimal places is 0.82. Now if we refer to this plot, then we will not find the elevator angle for CL equals to 0.82. So we will have to infer it from the values that can be directly read in this plot. So in this table here, I have made a list of the lift coefficient at trimmed conditions and the elevator angle at trimmed conditions. So if you look at the lowest line, then the value of CL trim is 0 and the elevator angle is 5 degrees. Next line crosses the horizontal axis at 0.25 and the elevator angle is 0 degrees. After that we have CL equals to 0.5 and delta equals to -5, then CL equals to 0.76 and delta equals to -10, and the final value is CL equals to 1 and delta equals to -15. Now what we can do is we can make a plot of delta trim as a function of CL trim, and we can fit a model on this scatter plot. And when we have the equation for the model, then we can calculate the value of delta trim for CL equals to 0.82. Now in order to plot this data and obtain the fitting function, I wrote a short code in Python. So I am going to try a linear fit. So y equals to mx plus c. Here I have provided the values of the lift coefficients, and here I have provided the values of the elevator angles, and I'm doing a curve fit using the code in this line, and the fitting parameters, which are the slope and the offset, are stored inside this POPT array. So I'm going to plot both the data as well as the fitted function, and you can notice that as we had expected, the delta trim as a function of CL trim is a straight line, so the linear fit is valid. Now we can also obtain the equation for this line, and as I mentioned already, the coefficients in the equation m and c are already contained inside this POPT array. So if I want to know the value of the elevator angle, CL equals to 0.82, I just calculate the value of this function, and I get minus 11.3 degrees. So the required solution is minus 11.3 degrees. So either you can write a code and follow the process that I did, or I think it should be fine even if you just do a linear interpolation between these two data points. The reason I wrote the code was initially I was not entirely sure if the data will follow a linear pattern. Also, I was not entirely sure if my readings of these plots would be reliable. So just to reduce the errors coming from the reading of the plot, and because I did not know whether delta trim would vary linearly with CL trim, I wrote this line of code, which can again be easily modified even if the relationship were not to be linear. But if you already know that delta trim as a function of CL trim has to be linear, then it should be adequate just to do a linear interpolation between these two final values. And it makes sense that the elevator angle is negative 11.3 degrees because the value of CL trim is between 0.76 and 1, and the value of the elevator angle that we found is also now between negative 10 and negative 15.